Alright, so today I'm gonna be explaining this important paper with the title, Is Graph Convolution Always Beneficial for Every Feature? This I cleared paper in 2025. Graph neural networks have demonstrated strong capabilities in processing structured data, while traditional GNNs typically treat each feature dimension equally during graph convolution. We raise an important question: is the graph convolution operation equally beneficial for each feature dimension? If not, the convolution operation on certain feature dimensions can possibly lead to harmful effects, even worse than the convolution-free models. In prior studies to assess the impact of graph convolution on features, people proposed metrics based on feature homophily to measure feature consistency with the graph topology. However, these metrics have shown unsatisfactory alignment with GNN performance and have not been effectively employed to guide feature selection in GNNs. We introduce a novel metric topological feature informativeness to distinguish between GNN-favored and GNN-disfavored features, where its effectiveness is validated through both theoretical and analysis and empirical observation. We propose a simple yet effective graph feature selection, which processes GNN-favored and GNN-disfavored features separately. To extend the convolutional definition of label homophily to node features, feature homophily metrics are introduced. The general form of feature homophily is here. So this eta is a normalization function and sim is similarity metric. Mutual information measures amount of information obtained about one random variable given another one. So this is the mutual information between two random variables. Here they show improvement in GNN performance at node level and feature level. Different colors denote node labels, while the direction and magnitude of arrows denote node features. We define a graph where V is a node set, E is edge set. For an undirected graph, its structure can be represented by an adjacency matrix A, and N is the number of nodes. A indicates the presence of an edge between nodes U and V. The node classification task on graph aims to predict node labels by utilizing node features and topological information where X denotes the mth feature of node U. So, to address the limitations of feature homophily metrics, we propose this topological feature informativeness to measure the informativeness of neighbors in graph given feature X, which can be expressed as this. And it leverages mutual information to quantify a degree of dependence between variables, thereby revealing both linear and nonlinear relationships. So you see in figure 3 that for each feature dimension, we first measure its corresponding TFI. And higher TFI indicates stronger GNN performance compared to MLP. We apply a threshold to select the set of GNN favored features. Then we concatenate the MLP and the GNN features, and then through linearity, this is the framework of GFS. So the GNN favored XG, the GNN disfavored, we call it X, not G, are better suited for MLPs. When it is disfavored, we use MLP. Then we concatenate, as I said, and that's a good representation. They did experiments on different data sets and different models. For example, graph attention, and GFS. For example, APPNP and GFS. They want to see what happens if they add this framework.